Hello everyone. The title of this video is Find the Value of a Function. And in this video I have, I believe, 22 examples set up. We're going to be looking at a function expressed in function notation and asked to evaluate such a function for certain inputs. So, for the examples in this video, I am taking problems directly from a free online textbook at openstax.org. This textbook is Intermediate Algebra, 2nd edition. And the section I'm working in is 3.5, titled Relations and Functions. And I'll be working on exercises 307 through 328. All right. So example 1 will be 307, example 2 will be 308, etc. all the way down to example 22 being number 328. So if you'd like to follow along, or if you'd like to see a particular example, just count down how many numbers it is and look for that example number in the description of the video. I do have timestamps for each example. Alright, and one thing I'd like to say too, that I haven't been in recent videos, is if you want some extra practice, trying to get the material down yourself, before I even do an example, pause the video and try to work on it yourself. And then watch how I did it and compare and see how you did, and hopefully you'll learn something as you do that throughout the examples of the video. Alright, so for first several problems, we're asked to do the following. We're asked to evaluate the function and find the following three: f of 2, f of -1, and f of a. Alright, so before I get into the first example, let's talk a little bit about this function notation. So when you see f of x, right, this is pronounced f of x, right, not f times x, even though I know it looks like a multiplication thing. But in the context of whatever problem, you should know that this is function notation, f of x. Or g of x, h of x, f of t, it doesn't matter. Right? There'll be different letters, different names, different variables depending on the problem. We'll see later examples with different letters. When you see this, on the other side, what this is equal to is some expression that's dependent on the value of x. So an expression like 5x minus 3 in this first example, right? F of x equals 5x minus 3. When you see an f of x like this, x is the input variable or independent variable. F, the letter F, the letter in front of the parentheses, is just the name of the function. And it doesn't have to be a little f. It could be, again, little g, or an actual word like square of x or something like that. But this is just the name of the function. And then f of x all itself is the output. The dependent variable. So very often, f of x is a y value. Now, again, the variable name may change at some point, but in most cases, your input value is x, whatever's in the parentheses, and then f of x altogether is like the y value, right? If you were writing ordered pairs, x would be the first coordinate, f of x would be the y coordinate. So x comma y in ordered pair talk is exactly the same as x comma f of x. Right? I mean exactly the same thing. Or y equals f of x. Right? The output variable is whatever the value of f at x is. All right, so for example, again here, we have this f of x equals 5x minus 3. As I kind of pointed out, this is the same really as the following equation. This is the same as saying y equals 5x minus 3. Right? F of x, this represents y. F of x represents outputs. F of x represents second coordinates. Right. So first, find f of 2. What does this mean? This means find this f of 2, this is the output, or the y coordinate, when the input is 2. Right? So x is being replaced by 2, and then we say f of 2 is, again, just go through the rule, go through the expression for f of x, and replace all the x's with 2. It would be 5 times 2 minus 3, which is 10 minus 3, which is 7. Pardon me. So f of 2 equals 7. And this means, pardon me, wow, that the ordered pair 2 comma 7 would be on the graph of this function or belongs to function f. Because remember, a function is just a set of ordered pairs where every input, is assigned to exactly one output, right? Every value of the domain is assigned to exactly one value of the range. So when I say f of 2 equals 7, again, that means 2, the input 2, is assigned to the output 7, or the domain value 2 is assigned to the range value 7 in this function that's called f. So there's part 1, f of 2. Now the second part is what's f of negative 1? Okay, so again, take this function here, this rule. What negative 1 is a value from the domain. What would be the value it's assigned to in the range? Right? So f of negative 1, just go through, replace all the x's with negative 1. That'd be 5 times, and then instead of x, 5 times negative 1 minus 3. That's negative 5 minus 3, that's negative 8. So the value of f at negative 1, or f of negative 1, equals negative 8. That's the second response that we're looking for. And again, what this means that the ordered pair, negative 1 for x, negative 8 for y, belongs to this function called f. belongs to function f. And we could keep going with this. Right? Now, this last thing is just what's f at a? And all you're doing is just like with 2 and -1, is replacing x with a. So very simple last part. The value of f at x equals a is 5 times a, so 5a minus 3. Right. And there you go. And that's as simple as that gets. Now again, what this means that ordered pairs of the form, ordered pairs of the form, a for the x value, and then 5a minus 3 for the y value, belong to this function called f. Right. And then you could go through and replace a with any number you wish. If a were 2, you'd have 2, 7 is an ordered pair in f, which we already saw. Right? 2, 7 is in f. If a were -1, you'd have -1, -8. Right, replacing it with -1, -1, -8 is an ordered pair in f, which we've already seen. But you could replace a with anything you want, right? 0, -3, 5, 22, right? You could replace a with any value you want, and this will give you an ordered pair in this function. Very, very simple though to evaluate a function, find the output, find the value of a function at a certain input. Just go through the rule, replace x, replace the input variable with whatever's in parentheses, right? I replaced x with 2, I replaced x with -1, I replaced x with a, and got my output. I'm hoping that sounds simple enough. Alright, so example 2, we're asked to find the same 3 values, the same 3 outputs, but the expression is different, right? We have f of x, or y, equals 3x plus 4. So this describes how x is related to the output f of x, or how x is related to y in this function called f. Alright, so as before, what's f of 2? The value of f when x is 2, we'll just replace x with 2. That'd be 3 times 2 plus 4, which is 10. So the value of f at 2 is 10, and that means that the ordered pair 2, 10 belongs to this function, right? This set of ordered pairs called f, right? The name of the function f. And if we were to graph f, right, the graph would contain the point 2, 10. F of -1. Again, just replacing all the x's, all the input variable with -1. 3 times -1 plus 4. That's -3 plus 4, that's 1. So the value of f at -1 is +1. An alternative meaning is that the ordered pair -1, 1 belongs to function f. I hope we've seen these before. These just mean the same word as above, ditto marks. And the value of f at any value a is the same thing. Go through the rule and replace x with a. So that'd be 3 times a plus 4. And that's it. And all this, and something that has an equivalent meaning, is that an ordered pair a, 3a plus 4 belongs to f. And this is for any value of a. Right? If a were 0, you'd have the ordered pair 0, 4 belongs to f. That'd be on the graph of f. 5, if a were 5, 5, 19 would belong to f, and so on. Okay, example 3. Example 3, same three values, same instructions. The value of f at 2 is negative 4 times 2 plus 2. That's negative 8 plus 2 is negative 6, right? So the value of f at 2 is negative 6. That's all they're asking for, negative 6. Now again, what that would mean, if you're talking about function f, now I'm going to do a little shorthand. This symbol here, kind of like a rounded little e, this means belongs to, or is a member of, or is an element of. Okay, so I'll use this like simple e symbol for belongs to. So if I say f of 2 is negative 6, that means the ordered pair 2 comma negative 6 belongs to function f. Again, the function is called f. And if I were asked to graph f, which I'm not, but the graph of f would have the point, negative 2 comma negative 6 on it. What's the value of f at negative 1? Again, just replace all the input variable with negative 1. That'd be negative 4 times negative 1 plus 2. That's 4 plus 2 is positive 6. So f at negative 1, or f of negative 1, is positive 6. There's the second output we were asked for. And again, this isn't something I'm asked to do. I just like pointing it out. All right, you can stop here if you were asked for the value. I'm just pointing out an equivalent meaning. If f at negative 1 is 6, that means x value negative 1, y value 6. So the ordered pair negative 1, 6 would belong to the function f. All right. And finally, for this example, the value of f at a, and just replace x with a. Be negative 4 times a plus 2. And that's as simple as that would get. Right. And again, all this means is that a for the input, comma, negative 4a plus 2 for the output belongs to f for any value of a. You could replace a with any number, right? If I replaced a with 2, I'd get 2, negative 6. If I replaced a with negative 1, I'd get the ordered pair negative 1, 6. Replace a with 0, you'd have 0, 2 was another ordered pair in this function, and so on. All right. Example 4. All right, same three outputs I'm asked for, same three values. So what's the value of f here at 2? That'd be negative 6 times 2 minus 3. It's negative 12 minus 3, negative 15, right? So the value of f at 2 is negative 15. And again, something that has an equivalent meaning is the ordered pair 2 comma negative 15 belongs to, right, the little sideways e symbol means belongs to, one more time, belongs to this function called f. Right. The value of f at negative 1 would be negative 6 times, x is now negative 1 minus 3. That's positive 6 minus 3 is positive 3. So the value of f at negative 1, or f of negative 1, however you want to say that, is positive 3. And once again, something with an equivalent meaning to this statement is that the ordered pair negative 1 comma 3 is an ordered pair in the function f. And then the third of these, f at a, again just replace x with a, is negative 6 times a minus 3, and that's as simple as that expression would get. And once again, something with an equivalent meaning to this statement is that any ordered pair that looks like this, input A, output negative 6a minus 3, would belong to the function f, and this is for any choice of a. Right, replace a with 2, you'd get the ordered pair 2, negative 15. Replace the a's with negative 1, you get the ordered pair negative 1, 3. Replace a with 0, you'd get 0, negative 3 belongs to f, and so on. Right, replace a with any legitimate value. Alright, same three values, but for this function now. So now f is this function that takes the input x and then squares it, subtracts itself, and then adds 3. X squared minus x plus 3. So again, f of 2 would be 2 squared. Notice I personally like putting parentheses around what I replace. Just a nice habit. Minus 2 for x, and then plus 3. And then doing the order of operations, 2 squared first, that's 4. Minus 2 is 2. Plus 3 is 5. All right. So the value of f at 2 is 5. Again, something that's equivalent to this is to say that the ordered pair 2 comma 5 belongs to this function, which is called little f. Alright, then the value of f at negative 1, and replacing x with negative 1, negative 1 squared instead of x squared, minus negative 1 instead of x, and then plus 3. Now remember, negative 1 to the second power is positive 1. That's negative 1 times negative 1. So I have positive 1 there, positive 1 here, right? Negative minus negative 1. So 1 plus 1 is 2, plus 3 is 5 again. So the value of f at negative 1 is also positive 5. And again, an equivalent statement to this would be that the ordered pair negative 1 comma 5 belongs to this function we're calling little f yet again. Then the value of f at a, again, just go through, replace all the x's with a. So it'd be a squared minus a plus 3, and that's as simple as that expression gets, right? There aren't any like terms to combine. And again, an equivalent statement to this would be any ordered pair that looks like the following: a for the x value, comma, and then a squared minus a plus 3 for the output, the second coordinate. This ordered pair belongs to the function called little f. Okay, so I'm going to stop doing this now with the ordered pairs belonging to the function. I'm hoping by now you understand this. So now I'm just going to write down from here on out the values that they're looking for. All right. So example 6, still the same three values being asked for. What's the value of f at the input of 2? What's the value of f at the input of negative 1? And what's the value of f at the input of a? So here f of 2 would be 2 squared, right? Just replacing all the x's with 2, plus 2, minus 2. 2 minus 2 is 0, so all I'm left with is 2 squared, which is 4. Right, so the value of f at 2 is 4. And that's it for part 1. This also means, that the ordered pair 2 comma 4 would belong to this function little f. But I'm not going to write that anymore as I did in the first 5 examples. All right, then f of negative 1. What's the value? All right, so when the input's negative 1, again, just replace all the input variables, all the x's, with negative 1. So it's negative 1 squared plus negative 1, right, instead of the x, and then minus 2. negative 1 squared is positive 1, plus negative 1 would be 0, and then minus 2 would be negative 2. So the value of f at negative 1 is negative 2. And the ordered pair, negative 1 comma negative 2, right, would belong to the function. And the value of f at a, again, just go through, replace all the x's with a. So that'd be a squared plus a minus 2. And that is as simple as that gets. Right? Doesn't, no like terms to combine or anything like that. Okay. Examples 7 and 8. All right, example 7, the same three values are being asked for: f of 2, f of negative 1, and f of a. So f of 2, right, that'd be 2 times, and then instead of x squared, right, 2 squared, minus, instead of x, I got minus 2, and plus 3. Square first, that'd be 4, then multiply. 2 times 4 is 8, then 8 minus 2 is 6, 6 plus 3 is 9. Right, so the value of this function when the input is 2 is 9. Right? And so if you were graphing or writing down the function as a set of ordered pairs, the ordered pair 2 comma 9 would be part of that function, this function little f. F of negative 1, again just replacing all the x's here with negative 1. Be 2 times, and then instead of x squared, right, we have negative 1 squared, minus, and then again instead of x we have negative 1 as the input, plus 3. Square the negative 1 first, making positive 1, times 2 would be 2, minus negative 1 would be plus 1. 2 plus 1 is 3, plus 3 again would be 6. So the value of f at negative 1 is positive 6. And if you were again listing ordered pairs that belong to this function little f, the ordered pair negative 1 comma 6 would be part of the function. And then f at a, just go through, replace all the x's with a. Simple as that. So it'd be 2 times a squared minus a plus 3. There you go. Alright. And then example 8, right, is the last example in which we're doing these three, and it's the last example, well, not the last one of the whole video, but it's the last one in this group where the function's called little f all the time. So we have f of x equals 3x squared plus x minus 2. First I'm asked to find the value of f at 2. So again, just replace all the input variables, all the x's with 2. 3 times 2 squared plus 2 minus 2. And this is going to be 12. Right? 2 squared is 4. 4 times 3 is 12. And then plus 2 minus 2 is just like plus 0. So we have f of 2 equals 12. And equivalently, right, the ordered pair 2 comma 12 belongs to this function called little f. And then we're asked for f at negative 1. Again, just replace all the inputs, all the x's with negative 1. So 3 times, and then instead of x squared, right, negative 1 squared plus negative 1 minus 2. Negative 1 squared is positive 1, times 3 is 3, and plus negative 1 is 2, minus 2 is 0. So f of negative 1 is 0. Right, so again, an equivalent statement to this would be that the ordered pair negative 1 comma 0 belongs to this function called little f. And then finally f of a, just replace all the x's with a. 3a squared plus a minus 2. Done. Okay, so those were exercise examples 1 through 8. Right, that's exercises 307 through 314 of the Section 3.5 Intermediate Algebra 2nd edition. Next, I'm going to work on exercises 315 through 320, which has some different instructions. We're still doing a lot of evaluation. All right, notice it's evaluate the function, find the following. You got 3 things. So now in these next several exercises, the function's name is little g instead of little f. But the way you do it's no different. And then what's g evaluated at an input of h squared, g evaluated at x plus 2. And then here, notice the difference between the second and third one, right? Here x plus 2 is in the parentheses. Here it's separated. G of x plus g evaluated at 2. Right, and we'll see that these are in fact different. Right? You can't just distribute functions. Right? And I'll point that out when we get to it. Alright, so example 9, we have g of x is 2 times x plus 1. So I take 2 times whatever the input is, and then add 1, and that'll be the value of g at that input. So first part, g of h squared would be 2 times, and then replace x with h squared. And since it's only got one term, h squared, I'm not going to put parentheses around it, and then plus 1. And there you go. And again, going back to what I did in examples 1 through 5, an equivalent meaning to this is that any ordered pair of the following form, h squared for the input, comma, and then 2h squared plus 1 for the output, belongs to this function called little g. And this is for any choice of h. Alright, so for example, if h were 0, you'd have 0 here, right, 0 squared, and then 1 here. There's an ordered pair in g. Right, 0 comma 1. G of 0 would be 1. If h were 2, you'd have 4 for the input, and then 9 for the output. This is another ordered pair that belongs to g. Right, and check it out. When I plug in 4 for x, don't I get 9 for the output? That's what this is saying. And I could do this all day long with, again, for any choice of h. Alright, then the value of g, part 2 here, at x plus 2. So just as all the other times, just whatever's in parentheses after the name of the function, that's the input. And that's going to replace the original input. That's going to replace x everywhere. So g of x plus 2 is 2 times, and then instead of x, got this. Got x plus 2 as the input instead of x. Plus 1, and again, there are, x plus 2 is multiple terms. That's why I'm putting parentheses around that. And then we simplify this a tad, right? I can distribute the 2. And we're getting the following. 2x plus 4 plus 1, that's 2x plus 5. When you combine like terms and do all the simplifying, right? So g at x plus 2 is equal to 2x plus 5. All right, then once again, what this means in relation to function little g is that any ordered pair of the following form will belong to g, where the input is x plus 2 and the output is 2x plus 5. All right, this will belong to g for any choice of x. And go ahead, let's try it out. Now just to show you that we get ordered pairs the same up here, what if x were negative 2? If x were negative 2, you'd have 0 for the input, 2 times negative 2 is negative 4 plus 5 is 1. 1 for the output. This is a ordered pair in G, and check it. When the input is 0 in this function, the output would be 1. That is correct. When x equals positive 2, we get, 2 plus 2, we get 4 for the input. 2 times 2 is 4 plus 5, we get 9 for the output. Hey, exact same ordered pair I got earlier. This is saying when the input of this function is 4, the output is 9, which is going to happen. Right? When x equals 0, and you can do this all day long. You'd have 2 for the input, 5 for the output. That's another ordered pair of G. And let's check it. If 2 was the input, 5 would be the output, right? 2 times 2 plus 1. You can do this all day long. Right? But all they're asking for, though, is this, the 2x plus 5. What's the value of G at x plus 2? Is this 2x plus 5? And then the last part, this is a little different. Because we got G of x, we're asked to find G of x plus G of 2. Now G of x, we already know. Right? G of x is right here. It's this expression, 2x plus 1. So that's replacing G of x. Plus, and then G of 2, we see from here is 5. Right? When the input of G is 2, the output is 5. And you can check that, right? 2 times 2 plus 1 is 5. And we're asked to add these. Right? So I'm evaluating G 2 times. I'm evaluating it at x, giving me 2x plus 1. I'm evaluating it at 2, giving me 5. And then we're asked to add those, right? There's a plus between them. And 2x plus 1 plus 5 is 2x plus 6. And this is it. Right? Now, unfortunately, this doesn't give me really any ordered pairs, because this is not just a single G. Right? It's not just G of something equals something. It's one evaluation of G plus another separate evaluation of G. So I don't get really any ordered pairs out of this. But notice that the expression in the third part, when I did G of x plus G of 2, got 2x plus 6. Whereas G of x plus 2 was 2x plus 5. So hopefully you notice that those are not the same expression, right? G at x plus 2 was not the same expression, not equivalent to G of x plus G of 2. So that gives you an idea as to, oh wait, you can't distribute functions is all I'm saying here. You can't distribute function notation. All right, so in general, what I'm saying here is that, if I take a function called f and I have it evaluated at, x plus y, this is not going to be the same as the value of f at x plus the value of f at y. I can't just distribute the function notation, right? So be careful with that. And we'll see that also happening in the next several examples. Because in example 10, right, in example 10, I have the same, I'm asked to do the same 3 parts. All right, find G of h squared, find G of x plus 2, and then find G of x plus G of 2. And we're going to see that the second part and third part aren't going to be the same, all the time. I mean, there are some scenarios where they're equal, where distributing will work, but just know that it won't happen in general. Right. So the first part's simple enough. What's G of h squared? All right, just replace x with h squared. That's 5 times h squared minus 8. And there you go. And I'll just leave it at that. Now you can write the ordered pair thing if you want. Right? This would mean that ordered pairs of the form h squared comma 5h squared minus 8 would belong to this function called g, but I'm not going to write all that anymore. Then g of this x plus 2 input. And just replace x, wherever you see it, with the quantity x plus 2. So instead of 5 times x, we have 5 times the quantity x plus 2. And then minus 8. And you distribute the 5 and combine like terms. We'll simplify this. It'll be 5x, and then plus 10 minus 8. So it'll be plus 2. All right. And again, we can say an ordered pair thing that, any ordered pair of the form x plus 2, comma, 5x plus 2 will be in this function called g. But now let's say we what happens when we distribute the g here? Do we get the same thing? What's g of x plus g of 2? Well, if I evaluate g at x, I'm just getting what I started with, 5x minus 8. There's g of x, plus, and then the value of g at 2 would be 5 times 2, which is 10, minus 8, which is also 2. And combining like terms, you have 5x minus 8 plus 2, that'd be 5x minus 6. And notice again that g evaluated at x plus 2 was not the same expression, or is not equal to g at x plus g at 2. Right, so again, you can't just distribute function notation. You can't distribute the name of a function. All right, and same three things for example 11. All right, start flying now. What's g of h squared? Just replacing x with h squared, we have negative 3 times h squared minus 2. And that's as simple as that gets. Then we're asked to find the value of g at x plus 2. So again, you just replace all the x's with x plus 2. So negative 3 times the quantity, x plus 2, and then you have minus 2 after that. And we'll simplify, right? I'll distribute the negative 3 here. So we have negative 3 times x, and then we have minus 6 minus 2 be minus 8. And that's as simple as that gets. There's the value of this function when the input is x plus 2. It would be negative 3 times whatever x is minus 8. And then suppose we distributed the function name, even though you can't. Let's see what we get. What's g of x plus g at 2? Now the value of g at x is this given here, negative 3x minus 2, plus, and then the value of g at 2 is negative 3 times 2 minus 2. That's negative 8. Putting these like terms together, we'd have negative 3x minus 10, right? Minus 2 plus negative 8 minus 10. And there you go. And notice yet again, these are not the same. Right? That's going to happen quite often. Again, reinforcing the fact that you can't distribute function names or function notation. All right, next example. Same three things asked for. G of h squared. Just replace the x with h squared. Negative 8 times h squared plus 2. And that's as simple as that gets. The value of g at x plus 2. Replace x with the quantity, x plus 2, so we have negative 8 times x plus 2, and then plus 2 again. Right. So this would be negative 8x, and then you have minus 16 plus 2 would be minus 14. And that's as simple as that gets. And then what's the value of g at x plus the value of g at 2? Well, g at x is given. That's this negative 8 times x plus 2 plus the value of g at 2 would be negative 14. All right, negative 8 times 2 is negative 16 plus 2 is negative 14. And yeah, putting the constants together, we'd have negative 8x minus 12. So notice it's a little off, right? Again, these are not the same. The value of g at x plus 2 is not the same as the value of g at x plus the value of g at 2. Once again, reinforcing that you cannot just distribute the name of a function. You won't get the same expression all the time. All right, same three things asked for in example 13. So what's g at h squared? It's just simply 3 minus h squared. And that's as simple as that gets. What's the value of g at x plus 2? That'd be 3 minus, and then the quantity, x plus 2, right? Replacing the x with x plus 2. Distribute the negative 1 here, and we get negative x plus 1, or 1 minus x if you want. And then what's g of x plus g of 2? Well, g of x, g evaluated at x is given, that's this 3 minus x up here, plus the value of g at 2 would be 3 minus 2, which is 1. And then combining these, we get 2 minus x, or negative x plus 2. Right. And yet again, we see that g at x plus 2 is not the same expression as g of x plus g of 2. Right. So once more, reinforcing the fact that you cannot distribute the name of a function. Alright, and then I have one last example where we're doing these three things, and then I have a few more after that. We're going up to 22. Alright, so the last example where the function name is little g here, and I'm asked again for the same three expressions. Right. So g evaluated at h squared would just simply be 7 minus 5 times h squared. There you go, and then none of those don't go together. That's as simple as that gets. The next one, the value of g at x plus 2 is going to be 7 minus 5 times, and instead of x, I have the quantity x plus 2. And distributing the negative 5 here, and don't forget the negative, that'd be negative 5x, and then 7 minus 10, right? Negative 5 times 2. 7 minus 10 would be negative 3. And there you go. That's as simple as that gets. And then the value of g of x plus the value of g at 2. Well, the value of g at x is this 7 minus 5x. Right? That was already given earlier. Plus the value of g at 2. Right, the value of g at 2. Let's see, it's 7 minus 5 times 2. 7 minus 10, that's negative 3. Right. And combining the constants here, 7 plus negative 3 is 4. So I have negative 5x plus 4. Right, and once again, we are seeing that the value of g at x plus 2 is not the same as the value of g at x plus the value of g at 2. Right? So again, just reinforcing once again that you just can't distribute the name of a function over the input. Okay, so those covered, that was exercises 315 to 320. And now I'm going to finish off here with exercises 321 through 328, where we're given some function with a specific name and asked to evaluate that function at a specific input, right, at a specific number input. All right, so the next example, example 15, all the way down to 22, I'm just asked to evaluate the function. All right. So number 15, the function's name is little f, and what it does, it takes whatever the input is, it squares it, multiplies it by 3, and subtracts 5 of it to get the output. Right. So we're asked to find f of 2. Right, find f at 2. So just replace x with 2 everywhere. 3 times 2 squared minus 5 times 2. Remember order of operations, right? You do the power first. 2 squared is 4. Then you do multiplication. 3 times 4 is 12. 5 times 2 is 10. 12 minus 10 is 2. So f at 2 is 2. Alright, and if you recall from earlier examples in the video, an equivalent statement to this would be that the ordered pair 2, 2 belongs to this function called little f. Alright, so if I were to add, if I were asked to graph little f, the point 2, 2 would be on the graph of that. Or if I was to write, the function little f as a set of ordered pairs, 2, 2 would be one of those ordered pairs. Input 2, output 2. All right. 16. This function's called little g. And g of x is 4x squared minus 3x. And we're asked to find g at 3. Right, what's the value of g at the input of 3? So I just replace x with 3 everywhere. 4 times 3 squared minus 3 times 3. Well, 3 squared is 9. 4 times 9 is 36. Minus 9 is 27. Right. So g of 3 equals 27. And again, an equivalent meaning is that the ordered pair 3, 27 belongs to this function called little g. Great. So continuing on with these kinds of problems. Example 17. Here we have a function called capital F. We have capital F of x, right? The input's x, whatever replaces x here, equals 2x squared minus 3x plus 1. And we're asked to find the value of capital F at -1. So I'm just replacing x's with -1. 2 times, -1 squared minus 3 times -1 plus 1. -1 squared is 1, times 2 is 2, then plus 3 is 5, and then plus 1 is 6. So capital F at -1 equals 6. An equivalent statement would be that the ordered pair -1, 6 belongs to this function called capital F. Number 18. We have a function called capital G of x, right? And the input's called x. Output's capital G of x. Equals 3x squared minus 5x plus 2. And we're asked to find the value of capital G at an input of -2. So that'd be 3 times, -2 squared minus 5 times -2 plus 2. And order of operations, right, simplifying here, -2 squared is +4, times 3 is 12. This would make +10 when I multiply. 12 plus 10 is 22, plus 2 is 24. Right, 12 plus 10 plus 2. So the value of g at -2 is positive 24. And again, an equivalent statement would be that the ordered pair -2, 24 belongs to this function called capital G. All right, so now we get into a little different one. Now, so far, in every single example, 1 through 18, the input variable was called x. But that is not always the case. All right, the input variable could be any letter we want, or even a picture of something. Right? All the variable is some sort of pictorial representation of a number. So here's a little different one. Number 19. The function is called little h. The input variable is t, not x. And notice that because it's h of t, a function of t, see the expression on the other side depends on t, not x. So h of t is 2 times the absolute value of t minus 5 plus 4. And we're asked to find the value of h when the input is -4. All right, so what's the value of h when, remember, this is when t is -4, not x. There are no x's here. Well, same thing. Anywhere there's a t, I replace it with -4. So we have 2 times the absolute value of -4 minus 5, right? Replacing t with -4, and then plus 4. So this is 2 times the absolute value. Remember, you simplify what's inside the absolute value first, and then take the absolute value. So that's 2 times the absolute value of -9 plus 4. The absolute value of -9 is +9, times 2 is 18, plus 4 is 22. So the value of this function when the input is -4 is 22. And again, something equivalent that means the same thing as this is that the ordered pair -4, 22 belongs to this function called little h. And I guess the only major difference now between this and previous examples is that this -4 is not the x value anymore. It would be called a t value, right? The input is t. And then the output is the h value, right? You could call it the y value since y wasn't used, but the output is just the value of that particular function, f, h, but usually it's also just referred to as y. Unless the input is y, like in 20. Look at example 20. We have a function called little h of y, meaning the input is called a y value here. So that might be a bit confusing. You won't see this too often. But the input is called y, so I'll call the input the y value, and the output I'll just call the h value because I don't want to call the input and the output the y value. That doesn't make any sense to call them the same thing. Alright, it's equal to 3 times the absolute value of y minus 1 minus 3. Alright. Find the value of h at input -4. Again, this is the input value. It's going to replace y here. So it's 3 times the absolute value of y. Y is replaced by -4, and then we have -1, and then -3 after that. This is -5, right? The absolute value of -5 is +5, times 3 is 15, -3 is 12. So we have h of -4 equals 12. Right. And again, an equivalent statement to this would be that the ordered pair -4, 12 belongs to this function called little h. All right, and a huge difference here is that this first coordinate for this function, the way it's set up, would be the y value. I know it's weird looking, but it's whatever the input is the first coordinate, right? And here the input variable is y. So the second coordinate I'm not going to also call the y value, right? I'm just going to call it the name of the function, right? The h value. Okay, so just be careful. Now for the last two, we have kind of what we were used to seeing in the beginning of the video. Got f of x, right? The little f is the name of the function, and we're back to having the input be called x, right, instead of y or t. It's equal to x plus 2 divided by x minus 1. What's f of 2? Right, so f of 2 is 2 plus 2 in the numerator divided by 2 minus 1 in the denominator. Numerator is 4, denominator is 1. 4 divided by 1 is 4. So the value of f at 2 is 4. And again, this is equivalent to saying that the ordered pair 2 comma 4 belongs to this function called little f. And here we're back to saying that the input is an x value. It's the value of the independent variable, the input variable. And the output, because I didn't use y for the first one, I can call that the y value if I want, right? As long as I don't use y twice. Usually the output of an ordered pair is called the y value, but we could also call it the f value. Right? You could also call it the f value because that's the name of the function. All right, and finally, last example, we have a function called little g, right, and the input variable is x. G of x equals x minus 2 for the numerator divided by x plus 2 for the denominator. And what's g of 4? What's the value of g at 4? So replacing all the x's with 4. We have 4 minus 2 in the numerator, 4 plus 2 in the denominator. So 2 in the numerator, 6 in the denominator. Now this reduces to 1/3. All right, so the value of g at 4 is 1/3. And one last time, this is equivalent to saying that the ordered pair 4 comma 1/3 belongs to this function called little g. And these values, the input is what we're used to, right? We could call it our x value, right? The input variable is x here. And the output, since the input wasn't called y, I could just call the output the y value, right? That's standard. But because the name of the function is g, you could also call the output here the g value, right? The value of function g at whatever the x value is. Right? Great. All right, so I hopefully watching me go over all these examples helps you out when you're working on similar problems. And thank you very much for watching.